All right. Morning, everybody. Welcome. We made it. It's April. We're almost there. 3 more weeks. Keep going strong. I feel it too. Semester that feels like it just will not end, but we're going to get there. We're going to do it together. Uh, how's everybody doing? Yeah, we all made it through April Fools. There were a couple good April Fools jokes this year, I think. A couple that I appreciated. Okay. I know things have been tough. I'm going to start us off as easy as possible. What is 1 plus 1? Who's got me here? 2. We got it. Excellent. Full points to Meshvi. See, everybody's already concerned. We're far enough into 1240 that you're like 1 plus 1. Let me go check documents and theorems. Is this in here somewhere? Did I miss it? Nope. I just want to add two numbers together. Started us off good, right? Meshvi believed. Wasn't trying to trick you. I really wasn't. Just wanted to know what 1 plus 1 was. Now I want to ask the harder question, which is the worm question. What is the domain of this function plus? Somehow plus is doing something like a function, right? There's some inputs, there's an output. Depends on the input. This is true. But what is a reasonable interpretation? Okay, good. Excellent. Got exactly what I wanted to see. So let's change colors. By the way, I was tired of all my markers being dead, so I went out and bought new markers. Look at all the fancy colors I have now. I'm so excited. Got to take them where you can get them. Is plus a function from the real numbers to the real numbers. What is the set of inputs? If this is true, then I should be able to write something along the lines of plus of 7. That's what it means to be a function from real numbers to real numbers. You input a real number, you get out an answer. But if I just write plus 7, it doesn't really mean anything. So this one, not quite. Right? It's not just plus 7. I need something with 2 inputs. Yeah, okay, so Jonathan's got an idea I like. It's like I need 2 copies of the real numbers. How do I fit 2 copies of the real numbers into one set? Because remember, functions, the domain of a function has to be a set. It can't be 2 sets. So how do we combine sets together? What we really want to write is something that looks like plus 1 comma 1. And this we can interpret to mean 1 plus 1 equals 2. So what is something like this? It's not a set. If it was a set, I would draw it with curly braces, and if it was a set, I couldn't have 1 repeated twice. What lets you repeat the same element twice? There we go. Awesome. We got there. Very good. What I want is r squared, which is something you may have seen in math classes before. This is the set of ordered pairs x comma y, where both x and y are elements of the real numbers. And we've actually called this another set already. This is the Cartesian product of the real numbers with themselves. So this squared is because we're doing r times r. But when I talk about multiplying sets, what I mean is a Cartesian product where I have this ordered pair. Each element of the ordered pair comes from the same set. So we usually write the plus sign in the middle, just sort of how we're used to it. But plus is a function from the real numbers cross the real numbers into the real numbers. And you can write plus in this way, plus of 1 comma 1. If you write it this way, this is called a prefix operator. Which is as contrasted with how we normally write it, which is an infix operator. And of course, because you are human, I hope, I didn't put up one of those prove you're not a robot things at the beginning of this class, but if you're a robot, you're also welcome, I guess. Because we're so used to this looks easier, right? This is what we're used to. This looks weird. I'm not going to try and tell you this is normal. But think about this from the perspective of programming a computer. If you're programming a computer, prefix operators have some nice examples. Let's say your computer reads a string. If it reads the plus sign first, it knows what function it needs to do. It knows what comes next is going to be two numbers that it has to add. Whereas if the first thing you read is a 1, and then you read a plus sign, you have to go back and figure out, oh, I'm adding the thing that came before my plus sign to the thing that comes after. It's a little bit of extra code. And so for that reason, lots of early calculators actually relied on this kind of notation, of prefix operation. And I'm talking really early, like even older than me. You had to enter things, and if you wanted to do a big long calculation, you would enter into your calculator something that looked like plus times plus plus times 7 for -3, 5, 7. I might even need one more thing. Yeah, and so this is a prefix operator. So this means you're adding together the result of multiplying together the result of adding together. Yeah, I think I need one more number. Right, so this would mean multiply these, then add this, then add this, then multiply by this, then add this. And it's very difficult as a human to see what's going on. But for a computer, yeah, I'm just reading left to right. I'm putting things on a stack and then pulling them off of a stack. For those in computer science, those are terms that you may come across or have come across. So a little bit about operator theory there. But the point I want to get to is this idea of functions that take as input two things. So these are called binary functions or binary operators. If f is a function from A cross A to B, f is a binary operation. which is in contrast with if G is a function from just a single set A to B, then G is a unary operation or unary function. Sometimes also monary, but I don't know. Not as big a fan of monary, but it's in the documents and definitions, theorems and definitions documents, so figured I'd mention it. Okay, so let's try and come up with some examples of binary and unary operations just to get a feel for what it is we're talking about. So I'm looking for unary and binary functions. And let's say this is unary is from real numbers to real numbers, and binary is from real numbers cross real numbers to real numbers. What are some common examples here? I'll give you a hint. We talked about one at the end of class on Thursday, because I was moving towards this example. Square function, good. Square function, unary or binary? Unary, good. F of x equals x squared. Ceiling and floor, very good. These are both good unary functions. Single input gives a single output. What else we got? What are some binary functions? X times y? Yeah? I got nothing against that. X times y, which we could also think of as the multiply operation. That's a times, not an x. Yeah, good. So we've got plus, we've got minus, and then falling into my trap a little bit. Min-max is good as well, but I want to talk about divide. It's easy to go, oh yeah, times, plus, minus, divide. But is division a binary function from the reals to the reals? I'll add min-max as well. Yeah, so we have to be careful, right? Division is a little bit tricky because dividing by 0. So not quite. So many colors, I don't know what to pick. We have to be careful. Divide 5, 0 is undefined. Because 5 divided by 0 is a problem. And functions are supposed to have exactly one output for every input. So, divide is a function in the sense that we just need a different domain. We have divide is a function from the real numbers cross the real numbers to a set containing the real numbers and also undefined, the string undefined. if you think about divide as a function from a calculator's perspective, this is the set of outputs that can happen. If you put in two real numbers, you'll either get out a real number or you'll get out undefined or some error from your calculator. It'll tell you divide by 0 error, or something else will happen. And if we add this as an additional possibility, now this becomes a function. But functions are tricky like that. And so we want to capture this notion. And so a closed binary function is a function in which f of a cross a is a subset of a. And so all of our other examples up here, multiplication, addition, subtraction, min, max, all of those are going to be closed on the real numbers. They're actually also all closed on integers or complex numbers. Well, not min, max, but yeah, a little bit more complicated. And so closed operators are nice. You don't have to worry about this undefined extra case stuff. And so the field of mathematics where we study closed operators has a name. And I'm going to tell you the name, but I want to justify it a little bit, because sometimes it makes people a little angry. In grades 1 and 2 and kindergarten, and I guess maybe even grade 3 and 4, I don't remember. It was a long time ago. You learned about these functions. You learned about how to add numbers, multiply numbers, subtract numbers, even divide numbers ultimately. And then at some point, they got rid of your numbers. They took away your numbers and they replaced them with letters. This is the part where my mother says she lost track of math. She liked it up until they took away her numbers. So you had things like 3 plus 4, 2 times 7. And you were like, I'm on top of this. I can solve these all day. And then they said, okay, but what about x plus 4 equals 7? They replaced your numbers with letters. And this was called algebra. Right, spoiler alert for anybody who hasn't made it that far in math yet. You'd have 7y equals 14. And this was the study of equations. It generalized this basic idea and let you do things in reverse, or described a set of equations, especially if we had multiple variables. This now describes a whole set of numbers for which this is true. So the field of mathematics, where we study closed operators, is also called algebra. Because all we're doing is, instead of replacing the numbers with variables, we're replacing the plus sign with a variable. We would write things like x, or even make life even easier, 3.4. Dot is a closed binary operator from, let's say, the integers squared to the integers. And so what is 3.4? I can make it whatever I want. 11. And I can figure out what properties this binary operator has to have. So let's talk about some of those properties that we might be interested in general binary operators. One of them is called commutative. So a binary function is commutative if f of a comma b is equal to f of b comma a for any a and b in my set. So this is a binary function f from a cross a into a. So if you think about functions, we're used to things that are commutative. In fact, if we peek back at our examples of binary functions, times a times b is the same as b times a, plus a plus b is the same as b plus a. But minus a minus b is not the same as b minus a. Those are different. So in algebra, sometimes called abstract algebra, to differentiate, there's something different between plus and minus. Plus, it doesn't matter what order you list them in. Minus, it does. Plus is commutative. Minus is not commutative. Another property we might be interested in that looks a little bit more complicated. Do you need parentheses? So a binary function again, I'll say f from a cross a to a is associative if for all a, b, and c in a, f of, so f takes two things as input and spits out one number. One of the things I'm going to give f as an input is c. The other thing is the output when I plug a and b into f. So this looks complicated. And I'm going to ask, is this equal to f of what happens when I plug in a and the output of f of b and c? Now this looks like a crazy condition. Why would this ever be true? Except that what this is really saying, or an example of what this is saying, is, for example, a times b times c is equal to a times b times c. Multiplication is associative. Addition is associative. Plus of ab comma c is equal to plus of a plus of b comma c, which is the prefix operator way of writing a plus b plus c is equal to a plus b plus c. So associativity looks complicated. It's something we've seen before. It's something that you're familiar with. Just written in a new way. So binary functions can be commutative or not. They can be associative or not. So let's check understanding. We know subtraction, not commutative. Is subtraction associative? What do we think? No, right? We can come up with some pretty simple examples where this won't work. 1 minus 1 minus 1 is equal to 0 minus 1 is negative 1. But 1 minus 1 minus 1 is 1 minus 0 is positive 1. So no. Minus, not commutative, not associative. Another interesting property that these associative functions might have is an identity element. So if f from A cross A to A, and there exists a special element I in A such that for all A in A, I take any other element, f of I comma A is equal to f of A comma I is equal to A, then I is an identity of F. Okay, so let's look at some examples. Does plus have an identity? Yeah, good, right? If I have 0, then A plus 0 is equal to 0 plus A is equal to A. 0 is an identity of plus. Does times have an identity? Yeah, right? I can do 1. Does minus have an identity? Zero and some no's, right? Got to be careful. Zero does not quite work out. In particular, 1 minus 0 is equal to 1, but 0 minus 1 is equal to minus 1. So 0 seems like the thing we would want, but it does have to be an identity on both sides. The function does not have to be commutative. It's possible to have a function that's not commutative that still has an identity, but minus does not have an identity. Sorry, that pause was, did I want to go into an example of where that happens? But yeah. So let's let's leave that there. So I want to prove a theorem for you. Here's my theorem. if f from A cross A to A has an identity, it is unique. I want to prove to you that a closed binary operator can only have one identity. Okay. And the proof for this, something that comes up a lot. I'm going to just pick two different, or not different, I'm going to pick two identities of f. So suppose that I and j are both identities of f. Okay? So I'm taking two, and I'm taking them generally, right? Rule of universal generalization. No, specification. Just, I'm saying f has an identity. Let I be an element of the identities of f. Let j be an element of the identities of f. Not making any suppositions about I and j. Well, I know that f of I comma j, because I is an identity, this is equal to j. This is because I is an identity. But what else do I know that this is equal to? It's also equal to I. Because j is an identity. So I know that I is equal to j. So I picked any two identities of f, and it turns out that they're equal. I picked the same one twice. There's no way to pick two different identities. If I and j are both identities, then I is equal to f of ij is equal to j, so I was equal to j the whole time. You actually only picked one identity. There is only one. So it's possible for f to not have an identity, like minus. But if it has one, it only has one. There's no secret other number. That's kind of like 0. You can always add it and get back the same thing. There's no secret number like 1 that you can multiply by. 0 is special. 1 is special. They are the only ones with this property. Are we feeling good? Any questions? One more thing I want to mention about functions is that we can go beyond binary. So unary is f of a, and binary is f of a cross a. But you can have an unary function that maps f from a cross a cross a cross a total of n times into B. You're not restricted to only 2. You're not restricted to only using your function twice. So this is how we get things like functions that look like f of 1, 2, 5, 4, 8, 16. This is a function f on 5 inputs. And one common function like this are called projection functions. So a projection function usually written like this: pi sub I from A to the n, which just means A cross A cross A cross A to A, is a function that picks the ith coordinate out of your input. So here, f might be equal to pi sub 3. I am taking as input 5 numbers, and I'm projecting the third one as my answer. I'm not worried about the other numbers. They actually don't affect my answer at all. This projection function just takes the middle number. Or you can think of f of a to the 100, and I give you 100 numbers, and you spit out the first one and ignore the next 99. That would be pi sub 1. Questions at this juncture? Okay, in that case, let's take our break. Get up and stretch. So here we are using, okay, good, there are questions. We'll come back to the break in a second. Pi is a Greek letter. It is used for the constant that is, the ratio of the circumference over the diameter of any given circle. Right, circumference is pi times diameter, yes. So circumference divided by diameter is always equal to pi. But it is also still a Greek letter, which means we can use it as a variable. And it is frequently used as a variable to be the name of a function. Just like f is a variable is the name of a function, pi is the name of the function that we give to projection functions a lot of the time. Not always. It's not a requirement, but it is frequent. Another good question, what is the point of all of the other numbers? Frequently, when we end up using projection functions, it is in concert with other functions. We want to do function composition, which we'll talk about, I think, on Thursday. And you want to do a calculation and then pull part of your calculation out. So this comes up frequently in computer science. Maybe you need to send all of these numbers to your function in order to do some calculation. And it ends up changing all of them. You send your function an array, you get back an array of new values, but you actually only care about one of those values. And so you'll use a projection function to pull out the part that you want. Yeah, indexing and slicing and things like that. Formal computer science uses projection functions all of the time. Because you can do things like your input is one tuple, one input value, one array, and you can use projection functions to pull different parts out of your array. So you might write a function like f of pi 1 of my input, comma, pi 2 of my input. And now you're just taking your first and second values from your input, but you can treat your input like it's just one value on the way in. So I don't want to go too far deep into computer science theory, but it's really interesting stuff, and there's a lot there. Okay, now we'll go ahead and take our break. So 2 minutes. We'll come back at 9:13 Winnipeg time. Get up, stretch, get some water, use the restroom, do whatever you got to do. See you back in 2 minutes. Okay, I got 9:13. Let's gather back together, refocus, push through to the end of the lecture. So I want to shift gears a little bit, and I want to talk about the hardest, easy thing in this course. The next topic I want to talk about seems so obvious that you're going to be like, how is this possibly going to be hard? And then, I promise you, you're going to be working on a problem, you're going to have no idea how to solve it, and then as soon as I tell you, oh, use this, you're going to be like, duh, it's always this. Okay, so here's the problem. Anybody have siblings? Anybody an eldest sibling with younger siblings? So I have a brother and a sister, and I'm the oldest one. And they're twins. So they're both the same age and 4 years younger than me. So there are 3 of us. And if you're in a family with 3 kids, the worst thing ever are treats that come in packages of 10. So when you have 3 siblings, and 10, in this case, I'm thinking of ice cream sandwiches. What's the problem? Only children don't get to answer. You don't understand. You'll never get it. People with siblings, what's the problem if you have 3 siblings and 10 ice cream sandwiches? The youngest. Youngest says the youngest gets 4. You fight over the last one. There is no problem. Oldest takes 4. The problem has already come up in chat. Who gets the last one? Right? So it is very clear that if you have 3 siblings and 10 ice cream sandwiches, someone gets more than the others. So some sibling gets at least 4 sandwiches. Yeah, right. The dad comes in and takes some, or you cut it into thirds, or all of these other examples that in the real world can come up. This is a mathematical theorem. It is called the pigeonhole principle. And if you thought my siblings and ice cream sandwich example was dumb, the pigeonhole principle is so dumb. If you have n plus 1 pigeons, and for some reason you're putting these pigeons into holes, I guess if you raise pigeons, the way you do it is you have like a big board, like this, and you give them little individual cubbies. And the pigeons live in these cubbies, but the mathematical theorem just refers to them as holes. So if you have n plus 1 pigeons and n holes, then some hole has at least 2 pigeons in it. That's it. That's the theorem. This is the pigeonhole principle. This is a theorem in this course, and it is way harder than you think it is. It seems simple. I'm going to give you a slightly more advanced version, just to try and justify it looking like a real theorem in this course. So I'll add at the end here, basic. The advanced version is if you have m times r plus 1 pigeons and m holes, then some hole has at least r plus 1 pigeons in it. And I'll even prove this for you, just to give you an idea. So the proof is by contradiction. Assume for sake of contradiction, every hole has less than or equal to r pigeons. Then we sum over all of the holes of the number of pigeons in that hole. Add up the number of pigeons in hole I, which we'll call h sub I, to get sum from I equals 1 to, I said I have m holes of h sub I. This is less than or equal to the sum from I equals 1 to m of r, which is equal to m times r, which is strictly less than mr plus 1. But I'm supposed to have mr plus 1 pigeons. So number of pigeons. I'm counting the number of pigeons in 2 different ways. One is by counting the pigeons in each hole. The other one is this is how many I'm supposed to have. This is equal to the sum I equals 1 to m of h sub I, which is strictly less than mr plus 1, which is equal to the number of pigeons, which is a contradiction. Oops. Okay. So this is the pigeonhole principle. If you have 10 ice cream sandwiches and 3 siblings, the ice cream sandwiches are my pigeons, the siblings are my holes. Some hole has to have at least 4 sandwiches, because this is 3 times 3 plus 1. So I have to have at least 3 plus 1 sandwiches in one sibling. It seems like I'm just making things more complicated. Let me give you some examples to show you how we use this in practice. So here's an example. You have 6 bills in your wallet. Maybe I should clarify, 6 Canadian bills in your wallet. Show that you have a duplicate. So for our international classmates and also for our Zoomer classmates that have Cash App and Venmo and have never actually held a bill in their entire life, Canada has 5 denominations of bills. There's 5, 10, 20, 50, and $100 bills. How do we prove a statement like this using the pigeonhole principle? What are our pigeons? What are our holes? Yeah, exactly right. We use the pigeonhole principle. Our 6 bills are pigeons. Our 5 denominations are holes. So some denomination accounts for at least 2 bills. There we go. Right, this is a proof using the pigeonhole principle. Still feeling pretty obvious. Hopefully this is not blowing your mind so far. So let's do something a little bit more interesting. Claim. There are 2 Canadians with exactly the same number of hairs on their head. So if I gave you this in a math class and asked you to prove it, what would you say? Oh, come on, guys. The answer's super obvious. At least 2 Canadians are bald. This is the whole question. I'm done writing the question. And proof, at least 2 Canadians are bald. Done. 0. 0 hairs. That's a joke. Okay, actual proof. It is true that you can probably find 2 bald Canadians, but let's ignore that for a moment. Or let's say there are 2 non-bald Canadians with exactly the same number of hairs in their head. Who's got a rough estimate of how many Canadians there are? $38 million. Close enough for what I want. Roughly a lot. I mean, you know, kind of a lot. There's 7 billion people on the planet. Not more than 50 million of them are Canadian. But let's say at least 20 million non-bald Canadians. This seems like a pretty safe bet. Okay. Here's a slightly tougher question. How many hairs do you think are on your head, roughly? Five. All right. For some people, this is a very, very easy question. So it turns out that most people have approximately one less than a moment ago. Yeah, fewer at the end of 1240 than at the beginning of 1240, because this course makes you pull all of your hair out. Most people have approximately 100,000 hairs on their head. But let's say that you could have up to 1 million hairs, so 10 times as much hair as average, right? That would be very thick hair. So how do we actually prove this? How do we use the pigeonhole principle to prove our claim? Canadians are pigeons. Jonathan Lee, banned for hate speech. No, exactly right. The people are the pigeons. What are the holes? Yeah, the number of hairs. The holes are the number of hairs, which we'll say lands between 1 and 1 million. So we have 1 million holes, but we have 20 million pigeons. And so not only do 2 Canadians have the same exact number of hairs, it is likely that you could find at least 20 people that all have the same number of hairs. And it's not bald people, it's not people with 1 hair necessarily. We're talking like a good solid room full of people that all have 112,813 hairs on their head, and they have no idea. They're just out there. You could be sitting in the same room as one right now. So by pigeonhole principle, there's no dash here. I don't know why I wrote that. At least 20 Canadians have the same number of hairs. Okay. A little bit less trivial, right? Takes a little bit of thought to see how to use pigeonhole principle. Once I explain it to you, though, straightforward. So let's make things harder again. You go to a yard sale. The yard sale only has 10 items for sale. Each one is priced between $1 and $100. And only whole numbers. Nobody's charging like $2.50 at a yard sale. Prove that there are two sets of items which have the same total cost. So buying this lamp and that baseball card is the same total as buying this chair, this picture frame, and that soccer ball. So this is a little bit tougher. You get a problem like this, and you're like, I don't know how to solve this problem. And every time you come across a problem and you're like, I don't even know where to start, the answer is pigeonhole principle. Maybe that's obvious at this juncture because it's all we're doing is pigeonhole principle questions, but I guarantee you there will come a day where you don't know where to start and you ask for help and the answer is pigeonhole principle and you'll be like, JD said this would happen. But even when I tell you to use the pigeonhole principle, not immediately obvious. What are our pigeons and what are our holes? So if we think about this for a little bit, what is the range of amount of money you could spend? So on one particular item, you can spend between $1 and $100. But what's the range you could spend at the yard sale? What's the total amount you could spend? So 10 to 1,000 is a good start, but you don't have to buy everything. Right? You're not guaranteeing that you're buying all 10 items. So 1 to 1,000 I also like. I especially like 1 to 1,000 if I'm the guy at the yard sale, because that means everybody who comes buys at least one thing. You're allowed to walk up to a yard sale and not buy anything. Don't let anyone tell you otherwise. There we go. 0 to 1,000. This is 10 times 100. If you walk up to this yard sale and you know there are 10 items, everything between $1 and $100, the least you could possibly spend is $0. You walk away with nothing. And the most you could possibly spend is $1,000. That's if all 10 items cost the maximum amount. If you walk up with more than $1,000, there's no way for you to spend it all. I mean, there is. I'm sure if you give the person running the yard sale money, they won't turn it down. But the idea is based on the sale price, you can't spend more than $1,000. So how many different sale options are there? How many different total amounts of money you could possibly spend are there? How many values are there in this range? How many numbers between 0 and 1,000? Yeah, there we go. 1,001. Because remember, we're only looking at whole numbers. Okay, there's 1,001 possibility. This 1,001 is going to end up being either our pigeons or our holes somehow. So let's think about which we want it to be. We want to show that there are at least two sets of items which have the same total cost. We've got 1,001 possible different costs. Are these 1,001 possibilities our pigeons or our holes? There are holes. Good. These 1,001 different possible total costs are our holes, which means we need to figure out what our pigeons are. If we want two sets of items to have the same total cost, what are our pigeons? Sets of items. Good. Our pigeons are sets of items. How many different sets of items are there? There's 10 items you can buy. How many subsets of 10 items exist? It's not 10 choose 2. 10 choose 2 is the number of ways that we can buy 2 items. 10 choose n, n is between 1 and 10 is close, although remember you can buy nothing. Always possible to buy nothing. How many subsets are there of a set with 10 elements? Two to the 10. Right? For each element in the set, for every item at the yard sale, we make a decision, buy this or no. So we have a 10-step process. Each step has 2 options, buy it or not, giving us a total of 2 to the 10 different subsets. So sets of items, 2 to the 10. What is 2 to the 10 without a calculator? Where are my computer scientists? Important value to know. 1024. Good. So I have 1,024 pigeons. I have 1,001 holes. By the pigeonhole principle, at least one hole has 2 pigeons. At least one possible cost has 2 sets of items. See? Getting trickier. Also, using ideas from previous in the course. All coming together. It's like we had a plan this whole time. Okay, I want to do one more example. This is going to look the most mathy yet. I want to find a subset of the numbers 1 up to 2n. And in this subset, I don't want any of the numbers to divide any of the other numbers. So a subset A of 1 up to 2n, such that for x and y in A, for all x and y in A, x does not divide y. So let's do an example. If n is equal to 3, I'm looking at the numbers 1, 2, 3, 4, 5, and 6. I want a subset of numbers where nothing divides anything else. I could pick, for example, A is equal to 2, 3, and 5. So 2 doesn't divide 3, 2 doesn't divide 5, 3 doesn't divide 5, and of course the other ways as well. 3 doesn't divide 2, 5 doesn't divide 2, 5 doesn't divide 3. So none of these numbers divide each other. How big can my set get? So here I managed to find a set with 3 elements. Five is already that number for the original set 2, is it not? So I want any 2 elements in the set to not divide each other. So yes, it's true that 5 doesn't divide any of these numbers and isn't divisible by any of these numbers, but I can't take the whole set because 2 divides 4. So 2 and 4 can't be in the set together because then 2 would divide 4. I want to pick any 2 and not have them to be able to divide. So here I had 6 numbers. I was able to get 3. I want to ask, how big can A possibly be? So 2n. So I don't think size of A can ever be 2n. Because if size of A is 2n, then it includes 1. And 1 is always going to divide 2n. So here's our first argument. Must have size of A strictly smaller than 2n, because if 1 is in A, nothing else can be. So I can't possibly fit everything in. What other observations do we have? Can you find an A that always works? Prime numbers. This is good. So if A is the set of prime numbers, less than or equal to 2n, well, less than 2n. 2n can't be prime because it's 2 times n. I guess unless n equals 1. Okay, less than or equal to 2n works. So this is a lower bound on the maximum size of A. I was just going for something like 2, because you can always do 2n and 2n minus 1, and they won't divide each other. So this is the problem. We'll start with this on Thursday. I want to dive deep into this problem, because right now, before we even started, this range was 0 all the way up to 2n. And now we've made the lower bound come down a little bit, because we know 1 can't be an A. And we've raised the lower bound. We know we can always find a set of size number of prime numbers. We'll come back on Thursday and we'll ask, how close can we get this upper and lower bound together? Can we find better and better arguments? No even numbers is a little tricky because 3 still divides 9, and neither 3 or 9 are even. But so I want you to think about this. We'll come back. We'll talk about it on Thursday. We'll start with this problem. We'll see what we can do. Thank you for appreciating my use of colors. I'm very, very proud of them. Okay, stop the recording here.